Hello, my name's Matthew Williams. I'm a scientist at the University of Edinburgh and at the National Centre for Earth Observation in the UK. The goal of this talk is to explore the potential for data to support diagnostics and forecasting of the terrestrial carbon cycle via data model fusion. And this understanding will be built by explaining and exploring an existing framework called CARDAMOM. But we start with a discussion of models. We start with the premise that all models are wrong, but some are useful. To be useful, we have to understand how wrong any model is and why. And to achieve that, models must be calibrated and validated against observational data with robust error statistics. Once uncertainty is quantified, models can become useful for understanding, prediction and control, which after all is why we do modelling. Those are our targets for any endpoint once models are constructed. We'll be focusing in this talk on systems models. And systems models have particular value in that they allow us to understand the multiple and interactive controls on ecological processes. For instance, if we're interested in modelling stomatal conductance, we know that this is a function of atmospheric conditions such as vapour pressure deficit. We also know that it's a function of soil moisture, but that changes and varies on longer timescales than do atmospheric conditions. So our model needs to incorporate the sensitivity and temporal variability in these drivers. But then there's also complex feedbacks. Atmospheric conditions in turn affect soil moisture and so affect stomatal conductance through that route. Stomatal conductance will determine plant growth. That will drive the development of roots and change rooting depth, and the depth of rooting will determine plants' capacity to uptake moisture from the soil and thus will feed back onto soil moisture. So we begin to see the development of feedback loops that are going to be unwinding over varied timescales and interacting with each other to create complex patterns of variability. So models that we'll be discussing today are attempting to incorporate and explain these sorts of feedbacks. In constructing a model, we are faced with trade-offs. In a perfect world, we would like our models to be general, so we could apply them anywhere. We would like them to be accurate, so that they represent the truth, and we'd like them to be realistic, so that they are tied to our understanding about ecosystems. But it's likely impossible to achieve generality, accuracy and realism. There are trade-offs. General models, one could argue, need to be lean. For global application, one needs to be able to apply models straightforwardly anywhere that one applies the models. Realistic models need to represent key processes, and as our understanding develops, there are more and more processes to incorporate. So this tends to lead to more complexity, which is anathema to the need for lean models for general applicability. And then for accuracy, models need to be calibrated to robust, unbiased data, and they need to avoid overfitting. So we need to be very clear about the noise and the signal in any data that we use for calibration. So these are the trade-offs that we're faced with. And these trade-offs play out in arguments about complexity. So for modelling a forest, there is a gradient of complexity in the models we could use. At one extreme, one could represent forests with individual trees and even locate their branches and foliage and root systems in a three-dimensional matrix to allow us to explore competition, growth, three-dimensional light environments, the partitioning of energy with changes in solar geometry. At the other end of the scale, we could represent the same forest by aggregated carbon models, where we lump all the foliage into a single pool, the wood into a single pool, and roots, for instance. So these are extremes, and there's some variety of different types of complexity that could sit in between these. The attraction to individual competition models, say, is there's the potential to connect to many more observational data, to inventory data that track the population dynamics of individual plants and their interactions with their neighbours. So with all that information, a complex model could be tied to our understanding at a very basic level. But at the same time, that demands increasing numbers of processes, numbers of parameters, numbers of state variables. So we're entering a very challenging computational environment. Aggregated carbon models, fewer state variables, fewer parameters, much simpler models. Are they better? This is an argument that's underway and at the forefront of current debates. Let's think about the processes that underpin carbon cycle models, and photosynthesis is a critical one, of course. The input of carbon into ecosystems is largely driven by the photosynthetic process, and we can represent this on, again, a gradient of complexity in modelling. At its simplest, we could represent photosynthesis using a light use efficiency model, where assimilation of carbon is equal to a single parameter, epsilon, multiplied by the absorbed light. And these types of models have been widely used for many decades and can produce reliable results. At the next extreme, or the far extreme, we could take the physiologically realistic models of researchers like von Kammerer, Farquhar and others, where they represent, as we can see in this diagram here, a whole set of processes that we know underpin photosynthesis. So here's a realistic model which deals with the diffusion of CO2 into the chloroplast, the production of high energy compounds in light reactions. They're used to drive enzyme-mediated processes of carbon fixation. These models generate an estimate of assimilation as a function of light absorption, temperature, which determines reaction rates, stomatal resistance, which determines CO2 diffusion, vapor pressure deficit, which is going to control that rate of diffusion, stomatal resistance, CO2 concentration, enzyme concentration, and others. So a huge variety and complexity about how photosynthesis can be represented. These models represent a steady state condition. So given certain drivers and certain conditions, whether it's the epsilon parameter or it's the enzyme concentration of Rubisco, these models will give us a steady state estimate of photosynthesis as a function of conditions and ecological states. For instance, the leaf area index in this case determines the interception of irradiance above the leaf of interest, so shadowing impacts. And this type of model will give you an instantaneous estimate of leaf photosynthesis. However, we're interested in how photosynthesis accumulates over a day, a growing season, how it varies between years, between seasons, between stands. So that requires an estimate of canopy photosynthesis, and that is a function of photosynthesis of multiple leaves, and those leaves interact with each other, of course, by affecting the light environment. So we need to understand how leaf area index affects the irradiance of every leaf, representative leaf in the canopy. We know leaf area index itself is varying on seasonal timescales, And that is a function of temperature, which drives phenology, but also leaf area index is a function of photosynthesis of the canopy itself, which generates the sugars needed to construct new leaves. So now we can see another of these feedback loops that we discussed earlier. And this again generates complexity because we have to scale from leaf to canopy, and we have to deal with temporal variability generated by phenological variation in leaf area index. So time and space scaling are introducing complexity. For calibrating models, eddy covariance data has provided us with rich flux time series. Incredibly valuable insights have been gained into the fluxes of carbon into ecosystems or in and out of ecosystems and exchanges with the atmosphere. So this is a time series of data at Bev Law's site at Metolius in Oregon for a few years. And you can see the seasonal cycle of these daily fluxes. Net ecosystem exchange is what is measured directly by the eddy flux instrumentation. And models have been used to convert this to ecosystem respiration and to gross primary production. And each symbol on there is a daily estimate, and you can see that there are gaps, but there's an incredible richness that shows you both seasonal variability that's very clear, but also day-to-day, week-to-week variability, which is driven by variability in irradiance and vapor pressure deficit. So there's lots of information that we can extract, and you see here we've calibrated a model. The black line here is a model that we've calibrated to fit the fluxes, and we're able to fit the fluxes and their component fluxes of respiration and photosynthesis. The states of stocks of carbon in this same ecosystem are sampled much less frequently. On the right hand side you can see there are a few estimates of foliar carbon, the symbols there with the error bars, of fine root carbon and a woody carbon, but they are typically about once or twice a year, if that, because it's time consuming and difficult, hard to automate this process. And yet it is of course the changes in wood stocks that determine whether the system is a source or sink of carbon. And in this particular case we can see that woody carbon is lightly accumulating, and we're able to model that accumulation. Again, the black lines represent the model that we've calibrated based on the data. The grey shading shows the uncertainty, and it largely includes the uncertainty on the observational measurement. But you can see the uncertainty is larger than on the individual fluxes on the left hand side where flux data are available. But what this emphasizes is that there's sparse stock data, and this can restrict our ability to estimate carbon sources and sinks. And a lot of the work, the rest of this talk, will be showing how we can use stock data, which are increasingly available from Earth observation, to try and make constrained estimates of the carbon cycle in places where we don't have eddy covariance systems, because these only sample a small fraction of the Earth's surface in very few locations. So this is our overall thesis, that models and observations carry useful information about the carbon cycle. Models are capable of interpolation and forecasts. This is their great value. We can ensure a mass balance. But the problem we have is that the models are subjective and inaccurate. They're wrong in all likelihood because they're just our best interpretation of a complex system. Observations, on the other hand, there's an opportunity to provide clear, confident estimates of the state of the carbon cycle. But observations are necessarily incomplete and patchy, whether that's in space because we have few flux systems, or in time because we lack long-term estimates or only have infrequent measurements of carbon stocks. And even with an eddy covariance system, we're only measuring net fluxes, and the decomposition into gross fluxes requires modelling with a set of assumptions in themselves. Fusing models and observations gives us an opportunity to generate an analysis, and that analysis has the potential to be complete because the model can fill in all the gaps in the data. It has the potential for clear confidence limits because the observations and their uncertainties can be propagated into the analysis. And it's capable of forecasts because we have a process model that allows us to extrapolate in space and time. The typical carbon model approach has been to generate a representation of the system of interest in the model, the green box in the middle here, to force it with climate, to set its parameterization according to land cover or plant functional type maps, some field studies. So in this case, a biome tends to have the same parameters wherever it is on Earth. The model is then spun up by simulating carbon stocks and fluxes over a long time period until some steady state is reached. And then the model is perturbed with recent climate or disturbance and compared to carbon stocks and flux observations. And at this stage we have a potential for benchmarking. But it's not always then clear, well, how do we improve the model based on those independent observations? We have questions about, well, are PFTs valid across the globe? How can we be certain that the PFTs we've applied in the Congo that are based on detailed studies in the Amazon are valid? And what's the model uncertainty? These models are often highly complex and the uncertainty on the process parameters is not well understood. There's not a clear process for propagating that into model forecasts. So the carbon model data fusion approach is an adjustment on what we've just seen. There's still a model, but now we don't spin up and we don't have PFTs. We have some prior estimates of the process parameters that come from field observations and the initial conditions, the stocks of carbon in each model pool. They also have some prior estimate. We force the model with climate. We generate estimates of stocks and fluxes at the target locations where we have independent stock and flux observations. And we look at the mismatch between the simulations and the measurements. And we look at the uncertainties on the stocks and fluxes. So we weight them according to how reliable the independent measurements are. And then we use an algorithm, and there's various possible algorithms, but in our case we use a Monte Carlo Markov chain Metropolis Hastings method to retain those parameters and initial conditions that produced estimates consistent with the observations. And then we resample from the hypervolume of potential parameters and initial conditions based on successful previous selections of those parameters. We sample parameter space and look for the parameter hypervolume that's consistent with observations. And we throw out those parameters that don't match the observations. We also use something called ecological and dynamical constraints, which I'll explain shortly. But that's the overall approach that we take. The advantage is that we end up with an ensemble of accepted parameters and initial conditions. And that means we can generate an estimate of the uncertainty on the model forecast because we can run the model across the full range of accepted parameters and initial conditions, and that means that we understand the uncertainty in our calibration and can propagate that into forecasts. So uncertainty is explicit and each location has local parameters. So instead of using PFTs, every grid cell of our calibration for which we have data, we can create a local calibration. And this means there's no PFTs. The model that we use in CARDAMOM is called Dalek, and it has various different flavors. This is one of the simpler versions, the Dalek CDA version. And you can see the pools are marked in green. There are 4 live pools, foliar, fine root and woody carbon pools, and then a labile pool, which you could think of as stored carbon or the carbon held in the buds. And the flushing of new foliage is driven by release of labile carbon into the foliar carbon pool. Photosynthesis is a function of weather, radiation and temperature, vapor pressure deficit. It's also a function of foliar carbon. You can see that dashed blue line. So there's an important feedback there. As a canopy thickens and develops, photosynthesis can increase. Photosynthesis, some fraction of that is respired, autotrophic respiration, and the rest is allocated to new buds and directly to foliage, roots and wood. Each of the foliar root and wood pools has a lifespan, a turnover rate, and that generates litter fall, plant mortality, and the dead organic matter from these pools is passed to a litter pool or a soil organic matter pool, and then these decompose with temperature controlled first order kinetics and generate heterotrophic respiration through decomposition. So it's a relatively simple model. We call it an intermediate complexity model. We can impose things like fire and management, so we can extract carbon if we have information on burns in any particular target grid cell or harvest operations. So there's a possibility for lateral removals of carbon from the system and then to explore what happens in the future post-disturbance. So the model data fusion system I've explained in broad terms. We have a random sampling of model parameters. We feed them into the Dalek model with climate forcing. We run over the full time period of interest, which is usually several years, running at weekly or monthly time steps. And here we're looking at how well the different parameter sets generate time series of leaf area index, and we look at their consistency, for instance, with the MODIS LAI time series and its uncertainty, and we accept or reject those parameter sets based on their consistency with the model, with the observation and its uncertainty. And we do this for multiple different observations when we have those. So Bayes' theorem allows us to generate a posterior parameter probability based on our priors, which are generated from the literature, and an observation likelihood given the parameters, which is determined by the model. The challenge we have is that parameter values span across multiple orders of magnitude, and we have multiple dimensions, so we have a huge parameter space to sample. But we argue that only a subset of parameter space can be considered ecologically consistent or sensible, and this can help us in our parameter search. So we do this with ecological and dynamical constraints. So we have a parameter vector for Dalek. Here I think there's about 23 variables, 6 of which are initial conditions we can see on the right hand side, and the others are various parameters about allocation, turnover and phenology. And we have in our EDCs various constraints that I've outlined here. For instance, the turnover rate of soil organic matter must always be slower than litter. The turnover rate of wood must always be slower than foliar carbon. These are just straightforward, sensible ecological constraints. We also make sure that the root-shoot ratio of biomass sits within broad but realistic domains or boundaries to avoid nonsensical ratios. And then we have dynamic constraints that ensure that we don't see really major shifts in the early part of our assimilation period, which would relate sudden shifts in parameters in variables because they're not consistent with fluxes. So this means that we tend to get a variety of salt and sink relationships if we don't have clear information in the observations that are assimilated. And we have order of magnitude constraint on proximity of the steady state, so we determine that for each pool. Now these can be relaxed if we think we're operating in an area where significant degrading is occurring or significant degradations occurring. The opportunity for cardamom comes about because we have vast expanding data sources. So biomass maps started being produced about 10 years ago, And we're moving into an era now where we will start to see biomass maps produced every year from new operational satellites like ESA's biomass mission or NISAR. The JEDI system from JPL is currently giving really exciting data over the tropics. Satellites like MODIS are giving us burned area information, so we have insights into where forests are being disturbed, combusted. LAI maps, MODIS has generated a long time series. Copernicus is now providing equivalently long time series, and the new Sentinel satellites are giving us unprecedented information on canopy reflectance and LAI. Soil carbon, not directly sensible from space, but there are lots of efforts to generate interpolated soil maps based on field data. So it's an exciting era where we're getting information largely on carbon stocks. There are, of course, information on fluxes being generated from atmospheric measurements, but I won't talk about those in this talk. But focus here is on how can we use information on stocks, their variability in space and time, to calibrate our models. So CARDAMOM. This is a terrestrial ecosystem carbon cycle analysis system. What CARDAMOM does is combine an assimilation algorithm, in this case the Monte Carlo Markov chain approach, and the EDCs, the ecological and dynamical constraints. It links those with a process model, in this case the Dalek model, and priors for their parameters. Climate and disturbance forcing can be added over the time period of the assimilation, and then we need data. So for instance, Earth observation time series if we're doing this across multiple pixels over the globe, but if we're running at a flux tower, it could be a time series from the instrumentation there. And the outcome for CARDAMOM is for any target site or grid cell is posterior parameter estimates and therefore model analyses with uncertainties. So we get a carbon state likelihood function, and we don't rely on any spin up, any PFTs, or any assumptions about steady state. And we produce ensembles, which means we have a direct estimate of uncertainty in everything that is generated. So for instance, in this pantropical analysis here, where we've assimilated all the data sets I showed earlier, we produce pixel by pixel modeled MPP that's consistent with the leaf area index. And we know that leaf area index is a key driver of production, of course. We produce heterotrophic respiration estimates in panel B that are consistent with the distribution of soil organic carbon. We generate emissions of carbon from fire that are consistent with the locations of burned area. And we generate, for instance, a net biome exchange that's consistent with biomass observations. And of course, each of these flux estimates in panels A, B, C, and D is consistent with all the data sources that have been assimilated because they're all connected to each other through the structure of the model. Now that of course means that the structure of the model is very important in determining the output, the analysis. But because Dalek is of intermediate complexity, it's quite straightforward to substitute different versions of Dalek with extra pools or fewer pools, with different representations of processes, different photosynthesis models, different phenological models. We could incorporate a water constraint. So the opportunity here is that we can also investigate model structural error by model substitution and comparing the uncertainty between models to the uncertainty within models in parameter uncertainty. So the outcome of a CARDAMOM analysis are maps like this. Here we have a global retrieval of carbon residence times in all the key pools. So the colour shading is based on the ratio of live biomass residence time versus dead organic matter carbon residence time. And we've just picked out 4 locations. T is a temperate forest, B is a boreal forest, D is a dry tropical forest, and W is a wet tropical forest. And on the right hand side you can see their panels and the estimated residence time of foliage, fine roots, wood, litter and soil carbon, and the uncertainties in each pixel. So you can see the box and whisker plots show you the variability, the uncertainty in each case, and you can see how the relative importance of different residence times, the relevant size of residence times, varies between these different systems. So in some cases, in boreal systems, you see that soil carbon has the longest residence time, but in the wet, moist tropical forest, you can see that the woody pool has a longer residence time. So this is the first time that this level of detail in residence time variability has been extractable from observational data. So that's one important usage of emergent diagnostic data that can help us understand carbon cycling globally. Another use of CARDAMOM is to look at the information content of data. In this case, we've looked at the uncertainty reduction in those carbon turnover times based on the assimilation of the biomass map. So we ran an assimilation with CARDAMOM, in one case with the Saatchi map of biomass and in another case without it. And you can see there is around 50% reduction in the 95% confidence interval on vegetation carbon turnover. And this uncertainty is spatially variable, much larger in some cases than others, particularly very disturbed areas like India, which has largely been cleared of its forests. You can see it has a strong reduction in the uncertainty of the turnover time because that's an area where it would have been likely heavily forested but has been cleared in many cases now. So we can gain an understanding about perturbation and non-steady state situations through these analyses also. Another outcome of the CARDAMOM analysis was to compare the spatial distribution of the parameters and look at their clustering against the 18 glob cover land cover types. So glob cover is just one of a variety of different PFT distribution maps that models often use to, typical models use to paint their parameters across landscapes. And what we can see here is that the glob cover land cover types are strongly correlated with some of the retrieved parameters, initial conditions, woody carbon, root carbon, foliar carbon, quite well correlated with glob cover. But the variability in the allocation fractions of net primary production to foliage, roots and wood is very poorly correlated with the glob cover types. That's not to say that the distribution of parameters across the globe from our CARDAMOM analysis is random or doesn't follow clear clustering. When we use empirical orthogonal functions, we can find very clear patterns and explain the variability of these parameters globally, as we see in the blue circles. So this suggests that land cover classifications don't match the emergent parameter mappings in important areas, and this means there are major challenges suggested for how current system models are parameterizing their PFTs. Just focus in on a Brazilian analysis that we've done, might be of interest. So here we focused at I think half-degree resolution across Brazil. We have observations, Copernicus time series, soil grids, carbon map, Habitabele's biomass estimate. And then we have drivers from the CRU data set on temperature, vapor pressure deficit, irradiance. We have information on forest loss fraction from the Global Forest Watch data set and burned area from GFED. So we have all this information that we drive the dynamic model with, and we use CARDAMOM then to generate calibrated outputs in each grid cell. These are the emergent parameter maps that come out of our analysis. So top right, you can see the biome maps for Brazil, and it's obviously a huge country. Large part of the tropics is contained in Brazil. The tropics are marked there with the dashed line. And you can see as you look between our emergent maps of parameters and the biome maps that there is a consistency, as one might expect, with for instance, the Amazon having clearly different estimated leaf carbon per area, so that's an important leaf trait, to the Cerrado and the Caatinga, these drier areas. And then the Atlantic forest, the Mata Atlantica forest in eastern Brazil, having actually more similar leaf carbon per area to the Amazon. Leaf lifespan, you can see differences again, a very clear boundary between the moist and dry tropics. Leaf nitrogen patterns, very clear difference there in the Caatinga between that and Cerrado, so there is also a clear difference in the ecological parameterization, the biodiversity that's emerging. Rather than being prescribed, we're seeing it come through our analysis. And if we look at allocation parameters, again, there are also clear patterns. So here we see the allocation of net primary production to leaves, to wood, and to roots. And these are expressed as a fraction. So we can see that in the Amazon, much of it is broadly similar allocation, around a third to leaves, to wood, and to roots. Although there is some variability within the Amazon, particularly perhaps along the rivers, along the Amazon and its tributaries, we can see different patterning emerging there, which is intriguing. And then when we move into the dry tropics, we can see that there's less allocation to wood and more allocation to roots. And this would be consistent with the dry conditions in these areas and the lower woody biomass. And you can see also the woody residence time is lower in the dry tropics, and there's some interesting patterns in the Amazon, which are of course of ecological interest. So this information could inform the development of improved plant functional type estimates for Earth system models. So what have we learned from the Amazon evaluation? Well, we see that the fractional allocation of NPP to different plant tissues shows clear emergent trade-offs across Brazil that are consistent with what we might expect, but help us to diagnose and understand the carbon cycle more clearly. And even within the Amazon, there's evidence of regional variability, with the northeast area having relatively higher allocation to wood and lower allocation to leaves. Now, this analysis is dependent on the Habitabile observations that we've used, and there are newer biomass maps being generated across the Amazon. So we need to look at how the data influences the quality of our diagnostics, and we need to have really robust error estimates on those observations so we weight our information appropriately. But there are spatial scale challenges. That analysis was at ½ degree across Brazil, but if we zoom in, here we're looking at some rapid eye images in Acre in southwestern Brazil for 2009 and 2015, and you can see the expansion of deforestation occurring with that typical herringbone pattern between these 2 years. And it's going to be important as we try and monitor and manage global forests to understand this fine scale disturbance, rather than treating each of these images as a single grid cell and lumping all the carbon. We're not going to fully understand the implications for ecosystem services and to make predictions of regrowth potential, reforestation, unless we understand at fine scales. So high resolution analysis is becoming more and more possible with the new instruments that we're producing. ESA's biomass mission will produce 4 hectare estimates of biomass every 6 to 9 months over its operational period. So we're hoping to see operational data at the resolutions that will help us pick out disturbance. The challenge then is, how do we model that? It's an enormous data challenge. But high resolution analysis, there's a huge opportunity here to use the information on ecosystem management and disturbance at fine scales to calibrate models at the scale of management and disturbance. And that means that carbon cycle diagnostics in near real time at ecologically and management human relevant scales becomes possible, and to look at the impact of management, track pest outbreaks, to better estimate degradation and regrowth in forests is all possible. There are major data challenges to managing the vast amount of information needed to do this. If we look to the opportunities that we have in the future, we've talked today about a carbon-only Dalek model that I've now outlined in orange here, state variables that it's tracked in the orange squares, and the black outline squares show that the processes that we've been tracking. But you could imagine also, we have also created a carbon plus water version of Dalek that also tracks water in soil pools and potentially could track water in live tissues. So we have information and modelling in canopy and stems below ground, and we track live and dead organic matter, processes, water content. And there's a very exciting opportunity in the future to bring a whole array of satellite observations to bear on constraining these processes and these pools. We've talked quite a lot about biomass data from radar and LiDAR satellites, and height data is also can be generated from these. We can constrain biomass pools, land use change, NPP potentially from these data, particularly time series. We've talked about optical reflectance data helping us constrain leaf area index and burned area, and that can also help with land use change. Spectroscopy data can give us column CO2, solar-induced fluorescence, exciting opportunity to potentially measure gross primary production directly. Radiometry can give us land surface temperature and vegetation optical depth, soil moisture, help us constrain estimates of biomass or moisture content of biomass. Missions like GRACE that measure gravity can give us information on deep soil moisture. So the future vision is how we bring all this information to bear on intermediate complexity models. There's a lot of work to be done on understanding and dealing with bias in these observations, so we don't end up just assimilating bias into our models. But models may also help us detect bias by connecting up multiple different data sources together and looking for consistencies between those. So in summary, carbon cycle data is growing exponentially. There's higher spatial and temporal resolution. It's more diverse in what's being measured. There's a huge opportunity to calibrate and evaluate process models, but Earth observation data errors need to be clear. We need to understand them and remove biases in those data. There's a massive challenge to maximize data value and develop knowledge, but we see an opportunity now to test alternate model structures much more efficiently, to understand model uncertainty and to propagate that. But there'll be a combined efforts needed from biogeochemists, ecologists, and remote sensing community, data scientists, and modelers in order to meet this vision. I'd like to acknowledge the help from the Global Change Ecology Group, and particularly Luke, Jeff, Anthony, and David, and the many data providers without whom we couldn't do this sort of work. I really appreciate the hard work that goes into generating these maps. And then funding, just acknowledge my sources of funding, and thank you for your attention.